So in the United Kingdom, we have over 350,000 metres cubed of cemented radioactive waste. That's about the same volume as one Wembley Stadium. This material is going to be radioactive for over 100,000 years. So a real challenge in trying to understand what we're going to do with the material is to try and understand how it's going to perform on very long timescales. What we have here is some Magnox swarf encapsulated in a cement material. Magnox swarf is the outer casing of a fuel pin, a little bit like this one. And what happens is the fuel pin gets chopped up into small tiny pieces, and these tiny pieces of the outer metal casing can sometimes contain some uranium. And this is very radioactive, and so we need to encapsulate it within something solid and safe. And so it goes into a drum, and it's filled with cement, and you get a waste form which looks a little bit like this. This means that we have a very large volume of waste, and it's also very radioactive. And so the preferred disposal option for this material is in something called a geological disposal facility. This is about 1 kilometre deep, and that's 40 times deeper than the London Underground. The geological disposal facility is a highly engineered facility which works on a process called the multi-barrier concept. And this is where we have several layers of containment to try and prevent water from reaching the radioactive waste and from the radioactive waste elements from leaching out to the environment. And it works a little bit like these Russian dolls here, where we have the waste is the smallest Russian doll, and this goes inside a waste container. The container is surrounded by a backfill material such as a cement, and then outside of the backfill material is the host geology itself. And we're interested particularly in the cement waste form itself and also the cement backfill material. So we're interested in trying to understand something called cement hydration. And this is when we have some cement minerals and we add some water, they start to dissolve. And when they dissolve, they create new cement materials, which make the cement a very strong and solid block. And this reaction can take place over 24 to 72 hours, but if there's still some free water left inside of the cement, this reaction can go on for years, maybe decades or longer. The secondary cement hydrate minerals are really important in nuclear waste immobilization because it's these minerals that will absorb the radioactive elements if they do start to leak from the waste and stop them from being transported to the environment. And so this is why we're here at Diamond Light Source, to try and understand this reaction using X-ray diffraction. So X-ray diffraction is a technique that can tell us about the atomic structure of crystalline materials. And the way that it works is we take an X-ray beam like the one here at Diamond, and the X-rays hit the atoms inside of our samples, and they're diffracted in lots of different directions and at different intensities. And these directions and intensities are specific to the crystalline material, so we can essentially use it as a fingerprint for that material, much in the same way that Rosalind Franklin used to identify the double helix structure of DNA. The really special thing about doing our experiments here at Diamond Light Source is that our cement samples can sit in front of the beam for 2 long years. And this is really important because normally the kind of experiments that we're trying to perform to understand the cement hydration reaction last usually 1 month or up to 1 year using techniques that aren't really very high resolution. Here at Diamond, following the experiments in situ, we can really get a detailed understanding of how fast the hydrate minerals are forming and exactly which mineral phases they are. And that's really important for trying to understand the safety functions of the geological disposal facility for nuclear waste.